In this video, we'll be discussing section 3.8, which is on implicit differentiation. And this is just yet another technique for finding derivatives. So far the techniques that we've covered will help us find the derivative of most things, but there are still a few that we're unable to find the derivative of. And really the goal of calculus is to be able to find the derivative of anything. So here we have another technique called implicit differentiation. And it's useful for non-functions. Or equations that have two variables in them. So a common example of that might be x squared plus y squared equals 1. So we have an x variable and we have a y variable. And let's say we wanted to actually solve this for y, put it in the y equals form in order to be able to find the derivative. We would subtract the x squared from both sides, and we'd take the square root of both sides. So we'd get y equals the square root of 1 minus x squared. Hopefully you're familiar with this very common equation. And this is the equation of the unit circle, or a circle centered at 0, 0 with a radius of 1. And if you actually graphed this right here, all you would get is a semicircle. Half of that. Not a great representation of a semicircle, but you get the idea. And the reason is that when we take the square root, we need to use plus or minus so that we can graph the top and the bottom and get a circle. And it's not a function. It doesn't pass the vertical line test where one x value actually matches up with more than one y value. So that's what makes this equation unique here. It's not a function, and if we were to put it in y equals form, it would actually take two different functions in order to express it. And that makes taking the derivative a little bit tricky. So if we actually wanted to take the derivative of this, we'd have to take the derivative of each part. And so our goal here is to be able to express the derivative with one equation, with a single equation. Alright, so that means putting it in the y equals form, not a great method, because we end up with two parts which make up the complete expression. Alright, so implicit differentiation is a way to get around all of this. It's so that we can express the derivative with a single equation. So let me first actually show you the process of using implicit differentiation for finding the derivative here, and then I'll summarize the overall steps of the process. Alright, so I'm finding the derivative. For x squared plus y squared equals 1. And you'll notice the notation that I used here, dy dx. That's important because since we have two variables, it's not clear which one we're taking the derivative with respect to. So this notation tells us that we want to do it with respect to x. So our final answer should be able to be written in the form dy dx equals something. Okay, so we'll keep that in mind as we work. Alright, so because these are summed or added together, I should be able to take the derivative of each part without needing a product rule or quotient or even chain, any of those fancy rules. So first off, I'm going to take the derivative of x squared, which is a simple power rule giving me 2x. But I'm going to show that I took the derivative of that variable x with respect to the variable x. And then I'm going to take the derivative of the second term, which will be a 2y. Here I'm going to show that I'm taking the derivative of the y variable with respect to x. And then lastly, on the other side, I need to take the derivative of that piece as well, and the derivative of 1 is 0. So that's the most important thing to remember with implicit differentiation, is that you can't forget to take the derivative of both sides or of every term regardless of what side it's on. Okay, a couple of things to notice here. First of all, I have a dx over dx. Now anything divided by itself is always just 1. So I really don't need that at all. The other thing to remember is, how do I need to leave my answer? Well, I wanted to find the derivative with the derivative of the function, or actually it's not a function, but the derivative of the equation with respect to x, and I wanted my answer to be in that form. So what I need to do is isolate this variable right here. And even though it's a complicated variable, it's still just a variable. So imagine isolating any variable. What you'd have to do is first isolate the term of the variable, and then isolate the variable itself. So the first thing I'm going to do to isolate the term is to take the 2x and move it over to the other side. And then lastly, I need to get the actual dy dx all by itself. So in order to make that happen, I need to get rid of the 2y, and because it's being multiplied, I can divide it away. So that leaves my final answer, dy over dx equals negative 2x over positive 2y. So it's not in the form that we're used to seeing in terms of derivatives. We've got x's and y's in our derivative answer, and that should happen when it's not a function and you've got both x's and y's in the equation. Alright, so basically what we need to do is take the derivative as usual, but we need to denote with each term what variable we used and what we're taking the derivative with respect to, and then ultimately we need to solve for that dy dx variable. So let me summarize that. Okay, so implicit differentiation summary. Alright, so first of all, you need to select the variable of differentiation. So in other words, what you're taking the derivative of with respect to. And so typically, we will choose x. And so we'll take the derivative of y with respect to x. And the reason we choose x is because x is the independent variable. Now that's not to say that it couldn't be done the other way around. That's just typically what we do. And you'll see a section coming up in the next several weeks where we actually have word problems that we need to solve using implicit differentiation. And some of the variables are things like velocity or radius or height or different things like that. And so you'll have to really read the problem in terms of what you're taking the derivative with respect to. It's not always just dy dx. But for problems like these, it usually will be. So just pay attention to that. Alright, the next step after that is going to be to take the derivative of every term. And I highlight the every piece because you do need to do it to both sides of the equation. Alright, and so you'll have to use chain rules and quotient rules and product rules and power rules and all the different rules that you have learned in the past. But take the derivative as you normally would, keeping in mind that you want to label each term as dy dx or dx dx, etc., so that you're labeling it which variable you took the derivative of and with respect to which variable. And then lastly, we'll solve for dy dx. Typically, just depends on the problem, but whatever it is we're looking to find, that's what we will solve for that variable. So I'm going to just give you a quick example here of why we've not used this in the past. And so I'm just going to call this a little side note here. Literally, side note. So let's say I have y equals 3x plus 5. Very, very simple expression, very simple equation. Well, we kind of did use implicit differentiation. We just didn't really need to use all the fancy notation because it was such a simple function anyway. So we use the dy dx notation here to say that we've taken the derivative. And essentially, think about what the derivative of y would be. It would just be a 1. And then implicit differentiation says we need to label that dy dx. On the other side of the function, take the derivative of 3x. Its derivative is 3. We took derivative of x with respect to x. So we're labeling it with that implicit differentiation notation. Here we're going to take the derivative of 5, and since it's a constant, it's just going to be 0. So in the end, we get dy dx equals, and then think about what's happening right here. As I talked about a second ago, or a minute ago, the dx over dx is really just a 1. So it's 3 times 1 plus 0, which is just 3. So we really are using implicit differentiation every single time we take the derivative. It's just that most of the time the notation is completely unnecessary. And so when we have non-functions, the notation becomes necessary. Alright, so that was my side note. Let me do another example. Alright, so here is my example. We've got x squared plus xy minus y cubed equals 7. Not a function. I've got x's and y's, and I would not be able to solve for y and get it all by itself and have a pretty little function. So I need to use implicit differentiation. And I'm going to declare that I want to find dy dx, which remember means that I want to take the derivative with respect to the variable x. Alright, so let's do it. So I'm going to take each term, 1, 2, 3, 4 terms, and I'm going to find the derivative of each piece, showing that implicit differentiation notation in terms of which variable I used and with respect to which other variable. Derivative of x squared is 2x. Took the derivative of x with respect to x. Here I need to take the derivative of this term, xy. That's a product rule. Alright, so I'm going to do the first term, x, times the derivative of the second, y, which is 1, except I need to show that I took the derivative. I took the derivative of the variable y with respect to x. Alright, so the first times the derivative of the second, plus the second times the derivative of the first, and again I'm going to use the notation showing which variable I took the derivative of and with respect to what other variable. Keep on going, take the derivative here, that'll be 3y squared dy dx, and I ran out of room, but on the other side I just get 0. Derivative of a constant 7 is 0. Okay, I'm going to run out of time here, so what I want you to work on before we head into the next video is simplifying and solving for dy dx so that you can get the ultimate derivative.